What is Loran? A system of long-distance navigation in which position is determined from the interval between signal pulses received from widely spaced radio transmitters. Loran, short for long-range navigation, was a hyperbolic radio navigation system developed in the United States during the World War II. It was similar to the UK ski system but operated at the lower frequencies in order to provide an improved range up to 1,500 miles with an accuracy of 10 seconds.
Loran was a hyperbolic radio navigation system that allowed a receiver to determine its position by listening to low-frequency radio. Signals transmitted by fixed land-based radio beacons. Loran combined two different techniques to provide a signal that was both long-range and highly accurate, features that had formerly been incompatible. The disadvantage was the expense of the equipment needed to interpret the signals, which meant the Loran C was used primarily by militaries after it was first introduced in 1957. By the 1970s, the cost, weight, and size of electronics needed to implement Loran had been dramatically reduced due to the introduction of solid-state electronics. And from the mid-1970s, early microcontrollers to process the signal. Low-cost and easy-to-use Loran units became common from the late 1970s, especially in the early 1980s. In the earlier, Loran system was discontinued in favor of installing more Loran stations around the world. Loran became one of the most common and widely used navigation system for large areas of North America, Europe, Japan, and the inter-Atlantic and Pacific areas.
History of Loran. The Loran or long-range navigation system was developed in the United States during World War II. It was similar to the British G system, but used lower frequency radio waves to give it a long range of as much as 1,500 miles. This longer range also resulted in lower accuracies, in the order of tens of miles, but this was deemed acceptable as it was decided the G could be used for the short-range navigation, whilst Loran would be utilized for the longer range. Loran was first used by ships and aircraft in the Atlantic theater, but eventually found more extensive use in the Pacific uses. It was first used for ships convoys crossing the Atlantic Ocean, and then by the long-range patrol aircraft, but found its main use on the ships and aircraft operating in the Pacific theater during World War II. Loran, in its original form, was an offensive system to implement requiring a patrol ray tube or CRT display.
So, this is our graph, where the vertices are V sub 1, 25,0, where the ship is located, and V sub 2, 15,0. And the foci are F sub 1, 35,0, where the station B is located, and F sub 2, 50, where the station A is located. Given the foci F sub 1, 35,0, and F sub 2, 50, given the vertices V sub 1, 25,0, where the ship is located, and V sub 2, 15,0. Find the distance of the ship from the station A. Find the standard equation of the hyperbola. A. Find the distance of the ship from the station A. Given V sub 1, 25,0 and F sub 2, 50. We will use the distance formula where square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Then we will substitute the given, where square root of 5 minus 25 squared plus 0 minus 0 squared. Then square root of negative 20 squared. Then square root of 400, where the square root of 400 is 20. Therefore, the distance of the ship from the station A is 20 kilometers. B. Find the standard equation of the hyperbola, given v sub 1, 25,0 and v sub 2, 15,0. We will use the midpoint formula where x sub 1 plus x sub 2 over 2 and y sub 1 plus y sub 2 over 2. Then we will substitute the given 25 plus 15 over 2 and 0 plus 0 over 2. Then 40 over 2 and 0 over 2, where our center is 20, 0.
The distance from center to one vertex is A. Consider C, quantity of 20, 0, and B sub 2, quantity of 15, 0. Use distance formula. Substitute A for D in the coordinates of points C and B sub 2 in the formula. Now, A is equals to square root of 15 minus 20 squared plus quantity of 0 minus 0 squared. Now, square root of negative 5 squared and square root of 25. Now, simplify the right side. Our A, the distance from center to one focus is C. Consider C, quantity of 20, 0, and F sub 2, quantity of 5, 0. Use distance formula. Substitute C for D in the coordinates of points C and F sub 2 in the formula. Now we have C is equals to square root of 5 minus 20 squared plus quantity of 0 minus 0 squared, square root of negative 15 squared, square root of 225. Now we will simplify the right side. Now our C is equals to 15.
In this problem, we need to find the value of B. So to find the value of B, we will use the formula of A squared plus B squared equals C squared, where A is equal to 5 and C is equal to 15. The first step, substitute the given value to the equation. So A squared plus B squared equals C squared will become 5 squared plus B squared equals to 15 squared. Then we need to multiply itself the value of A and the value of C. So it will become 25 plus B squared equals 225. After, we need to transpose 25 to the other side because we need to find the value of B. So the equation will become B squared equals 225 minus 25. We can also use the other way to have the variable B left. Write the same value like in this solution, 25 plus B squared minus 25 to cancel out 25 and have B squared. Lastly, our equation will become B squared equals 200 to cancel out the squared from the variable B. We will get its square root. So it will become the value of B is square root of 200. The graph opens to the left and right, we will use the standard form. X minus h squared over a squared minus y minus k squared over b squared equals 1. And from the previous computation, the given value for a is 5 and the value for b is square root of 200 and the value of c is 20 and 0. Next, we need to substitute all the variables value to the equation. So, the equation will become x minus 20 squared over 5 squared minus y squared over square root of 200 equals 1. As we can see, we can cancel out the square root from square root of 200 and cancel out its squared to have the positive 200. Therefore, the standard equation of the hyperbola is x minus 20 squared over 25 minus y squared over 200 equals 1.